7 key concepts demonstrated throughout the chapters: vertical asymptotes, holes, horizontal asymptotes, first derivatives, which are increasing and decreasing, second derivatives, inflection points, and full curve sketching. So let's start with vertical asymptotes first. So we see our function here, and right away we're not going to look at our numerator. Instead, we're going to set the denominator to 0 to find to solve for x. So once we solve for x, we have 2. Since the denominator is 0 at x equals 2, the factor does not cancel out. This means that the graph has a vertical asymptote at x equals 2. What is a hole? A hole is a missing point on the graph that happens when a factor cancels out in a rational function. So, once we have this function, we can simplify it into this. Then, after we simplify, we can cancel out our top with one of the bottom. We can cancel out a top function with a bottom function, meaning that left is x plus 2. So x cannot equal 2. That means that because the factor canceled, there's not a vertical asymptote. Instead, there is a hole at x equals 2. Now that we know there's a hole, let's find the coordinates of the hole. So we substitute x equals 2 into the simplified function, which is this function here, since we got the simplified function from our first function. So y equals 2 plus 2. Now we know that the function has a hole at the coordinates 2, 4. Horizontal asymptote is a line that the graph approaches as x becomes very large or very negative, showing the function's end behavior. So here's a shortcut that I've learned to help find horizontal asymptotes. So while looking at a function, if the degree, which is the denominator, is larger than the degree of the numerator, then y equals 0. And that's what you can see here. The degree of the denominator, which is 2, is larger than the degree of the numerator, which is assumed 1 because there is nothing here. So y would equal 0. Now we move to our second option. If the degree of the denominator is less than the degree of the numerator, then there would be no horizontal asymptote. Here we can see that x to the power of 2, meaning the degree is 2, and x to the power of 1, as I said before, we assume there's 1 here. So the numerator has a larger degree than the denominator, meaning that there is no horizontal asymptote. And finally, if the degree of the denominator equals the degree of the numerator, we divide the leading coefficient of numerator by the leading coefficient of the denominator. So as we can see here, x to the power of 2 and x to the power of 2, they have the same degree. So we then move to the leading coefficient, which is 4 and 2. So we divide 4 by 2, which equals 2. So we find a horizontal asymptote at y equals 2. Okay, so now let's find intervals of increasing and decreasing. So for increasing and decreasing, we know that it will be the first derivative of the function. So after we take the first derivative, we are left with this. Now we factor out the derivative and simplify it. We also, when we're simplifying now, we find the critical points. So now that we know the critical points are x equals 1 and x equals 3, we can make our sign chart and find out where the graph is increasing and decreasing. So, as we see here, our point 1 is right here, which is a point of inflection. And same with our point 3 down here. You can see how it's going positive and then turns to negative right at the point of inflection. And same with our other critical point here, 3. We can now find the interval of how we found these intervals was from plugging in numbers into our factored derivative. For example, if we plug in 2, which is higher than the number 1 and lower than the number 3, which means we're solving for the intervals of the numbers in here. So we plug in 2 for x into our factored equation, and we get a negative number. This means that the numbers and all the intervals in between 1 and 3 are going to be negative. Because the final answer is negative, all the numbers between points 1 and 3 are negative, which means decreasing. We can find other interval signs by plugging in numbers lower than 1, as well as numbers higher than 3. Now that we have our factored function from over here, we can see we can plug in our critical points into our original equation and find our local maximum and minimum points for the graph. So after plugging our first x value in, we have 4. So we solve for y here. So our x value is 1 and our y value is 4. We can also do the same with the second point. So plugging in 3 into the original equation comes out as 0. So we know our x value is 3 and our y value will be 0. So the local minimum is 3 and the local maximum is 1, 4. So now we can check this by looking at our graph. You can see the local minimum hits a 0, 3, and our local maximum hits a 1 and 4 point. Now, let's find concavity and our inflection point. So after we take the first derivative, we've seen up here in this earlier question, we can now take another derivative out of that, which is our second derivative. Now that we have our second derivative, let's look for possible inflection points. So we set the function equal to 0, and we solve for x. So x now equals 2. Now that we have x equals 2, let's plug it back into the original equation to find the y value for the inflection point. So after doing that, we find our y value, which is 2. So the inflection point is 2, 2. Now that we have our inflection point, let's plug in and test for concavity. So after we plug in, as we know before, our x value is 2. Now we can test values either under 2 and under numbers that are below 2 or numbers that are above 2. So after plugging in numbers, the values that I tested were 1 and 3, and I plugged them back into this equation. We found out that anything to the left of 2 is going to be negative and to the right is going to be positive. And you can see this reflected in our graph.
So I'm talking about 3.5, curve sketching of a rational function. So the function is f of x equals x over x minus 1. So first we determine the domain in vertical asymptote. The denominator is 0 when x minus 1 equals 0, so x equals 1. This value is not allowed, so it is excluded from the domain. Since the factor does not cancel, there's a vertical asymptote at x equals 1, and the graph will be split into 2 parts. Next, I find the horizontal asymptote. The degree of the numerator and denominator are both 1, as we can see here. So the horizontal asymptote is y equals 1, and the graph will approach this line but never reach it. Now I find the intercepts. For the x-intercept, I set the numerator equal to 0, and which gives x equals 0. This gives the point 0, 0. For the y-intercept, I substitute x equals 0 into the function, which also gives 0, so the graph passes through the origin. Next, I find the first derivative using the quotient rule. So the derivative is negative 1 over x minus 1 squared. The denominator is always positive and the numerator is negative, so the derivative is always less than 0. This means the function is decreasing everywhere in its domain on the interval from negative infinity to 1. And the graph starts near y equals 1 from below, moves downward as x increases, passes through the origin, and continues decreasing toward negative infinity as it approaches x equals 1 from the left. On the interval from 1 to infinity, the graph starts as a positive infinity just to the right of the asymptote, and we can see that right here. So as x increases, the graph decreases and approaches the horizontal asymptote y equals 1 from above. Since the derivative is never 0, there are no critical points. This means there are no local maximums or minimum values, and the graph never changes direction. Now to find the second derivative. The second derivative is 2 over x minus 1 cubed. So if x is less than 1, the denominator is negative, so the second derivative is negative, and the graph is concave down, as we can see in the graph as well. If x is greater than 1, the denominator is positive, so the second derivative is positive, and the graph is concave up. There's no inflection point because the function is not defined as x equals 1, and overall the graph has a vertical asymptote at x equals 1 and a horizontal asymptote at y equals 1. It passes through the point 0, 0, as we can see right here. Is always decreasing, is concave down on the left side and concave up on the right side. The left branch goes down toward negative infinity near the asymptote, and the right branch comes down from positive infinity and approaches y equals 1, but it's never touching. So we can see here that decreasing and the increasing, same as that one, that is still increasing and that is decreasing. The only difference is that is decreasing with the concave up and increasing with the concave up, and increasing right here with the concave down, as you can see that it's getting less and less, and decreasing with the concave down. So the important concepts are the asymptote, the vertical asymptote to the denominator equals to 0, and it does not cancel. For a whole factor cancels and a missing point. The horizontal asymptote, what the graph approaches at the end. Compare degrees to find horizontal asymptote. So top and bottom equals, so if bottom is bigger than top, it equals 0. If top equals bottom, ratio of leading coefficients, and if top is bigger than bottom, none, so it's slant instead. For the intercepts, x-intercept is set numerator to 0, and for the y-intercept is just plug in x equals 0. For the first derivative, find the critical points, and then set the derivative equal to 0. If it's positive, it increases. If it's negative, it decreases. And for the second derivative, if positive, it's concave up. If it's negative, concave down. For the inflection point, the derivative equals to 0 and concavity changes. And for curve sketching steps, domain plus asymptote plus intercepts, first derivative is increasing and decreasing plus max and minimum, and second derivative is concavity plus inflection, and then just sketch a graph. Now we have some practice questions for you.